Like I had said before, our goal for today is that we're going to graph, transform a little bit, and I'll explain that in a little bit too, and we're going to interpret something called the absolute value function. So, by way of review, what we did already was that we looked at this function right here, and we made a table of values with just a few points, and then we were able to plot those points and graph the corresponding equation, or the graph. Next, down here, instead of graphing by table of values, we spend our time using slope and y-intercept, and the green one over here shows me that. So at the -4, and I went up to right 1, up to right 1, plotted a few of those, or down to left 1, and connected those dots. The domain and range, as a reminder, domain and range simply just meant what types of x values are represented on this line. And we see that it goes forever in both directions, so we said all real numbers. Another way to write that is just use the symbol for real numbers. And the range is all real numbers as well, because it goes forever down. I'm looking at the black line here. It goes forever down, and it goes forever up as well. Turns out the green, it applies exactly the same for the green. The green line here goes up and down, left and right, forever and ever and ever, forever. It's a very long time. Now, absolute values. What are absolute values? To refresh ourselves, absolute value itself generally means, we usually say distance from zero, right? Distance from zero. So if you had a number line, you had 0, and you wanted to know, well, -10, what is its distance from 0? And so the way that we represented that was this. We did the absolute value bars, a -10 on the inside, and we know that that simplifies to 10 because the distance from 0 is 10. So, generally speaking, when we're talking about distance, we talk about absolute value. So we're going to see that later when we get to the application. But for now, let's just look at what a function might look like. So this function here is y equals the absolute value of x. So for all the values of x that we put in, we're going to get some output. So y equals the absolute value of -2, which just gives me 2. So if I were to plot this point over here, again, make sure to have some numbers for scale. Something like this. So at -2, it's a +2. Input a negative, out comes a positive. All right. Of course, when we substitute in, we get these expressions. We get a +1, a 0, a +1 again, and then a 2. So as we graph this, at -1, we get a +1. At 0, we get a 0. At 1, we get a 1. At 2, we get a 2. And we could keep going. Notice that the projection looks like this. We're going to go this way forever at what looks like a 45-degree angle. This is called my absolute value function. My absolute value function. Notice that the absolute value function is V-shaped. It's a V-shaped function, as opposed to linear, which always is just a line that never bends. So this is a V-shaped function. So let's walk through some definitions about this function here. So this function, y equals absolute value of x, is called, shockingly enough, it's called the absolute value function. I know, we mathematicians like to confuse you by calling things what they are called. There is a turning point. Notice, as I'm coming in from the left, la la la, I'm going down, sliding down, and then bam, I hit the ground and bounce off the ground like that. So there is a point where everything changes. First I'm going down, and now I'm going up. A dramatic change in my life. That, this guy right here, is called the vertex. And there's one more element in here. It's going to be a little bit hard for you to do without color because, and you'll see in a second here. Notice that I have, and I'm dashing this line, I have this line here, in this case it's the axis, that this line shows me that things just match up. It's almost like you set up a mirror right here and things reflect across it. Or if you were to fold this part over, it would fold and match up straight over there. So that line right there is called the axis of symmetry. I said the word bounce already twice. And you might think that this talks about like a ball bouncing, right? If I threw a ball down on the ground, it would hit the ground and bounce back up. And you would say, oh, maybe this looks like the path of the ball would go. Well, that's not quite true because if you were to toss a ball down on the ground, it might go to the ground pretty straight, right? Because if you threw it with strong force. But then the ball would do this. It would bounce up, and then it would loop back down like so. And then bounce up, and then it would go smaller and smaller and smaller. So notice, this is not really an absolute value right there, because it just bounces, and does this little arc thing, okay? It's called a parabola. So, a bouncing ball, this doesn't describe. But what can it describe? What path might the green thing follow? You have an idea?
Money.
Money? Oh, in what way?
Like, you could have more money than you spend it on, you keep spending it, and then you get, like, either your paycheck or a raise and you get more money.
Good, but in that case, I would have to be earning money per hour. Right, so at this point, I spent all my money, so I was not working, and I spent my money at the same rate. Then at this point in time, I said, oh, I got a job, and I started getting more money in, and they paid me every hour. Okay, that's kind of how it is. Or maybe it's a savings account, right? I depleted it, but then every month I put in a certain amount of money. Right, good, so that's a description. What about this? A hockey puck. A hockey puck comes sliding, hits the wall, and bounces off at the same angle. So this can describe a hockey puck. It can also describe a rooftop. Just can be a roof that can be steep or not steep, just like we did, if you remember, with the A-frame house, and we put on solar panels. So it could be a house, it could be a valley if it were strong, but mostly it's going to be distance away from something. So the domain and range of this is slightly different than the other one above. Notice domain is here. Notice if I were to shine a light from above, all the values here of x would match up, and all the values this way would match up. So all real numbers for the domain. There's no restriction. But what kinds of numbers come out of this? What kinds of numbers come out? Notice it's going down it's going up to infinity, and then down, down, down. It hits 0 and then bounces back up. So what numbers are excluded from this? What numbers do we never get to?
Negative.
We never get to negative. So my range is a good way to write this would be using the letter y. We would say y is greater than or equal to 0. It can be any number, positive, or 0, and it can be decimals, fractions, etc. Just can never be in the negative, as we are there. Now we're going to do a little bit of changing up. The idea of making changes to a graph, we can stretch it, we can shift it. So you don't have to draw this, but if I had a graph right here, and let's just pretend that I had a function that looked like this. I could take this v and I could move it around. I could have it exactly as I see it right here. I can shift it to the right like this. I can shift it to the left. I can move it down and up. If I wanted to get real crazy, I can make it larger. I could stretch it out. I can compress it a little bit. I could also flip this thing upside down if I wanted to. Flip it upside down as well. Okay? So I can do any type of change on a graph. That is called a transformation. So transform technically means to stretch or shift. When I say shift, you're just moving it left or right or up or down. When I say stretch, that means you're pulling it up, pulling it down, pulling it left, squashing it right. So technically you could squash it too. A stretch is a form of a squash. So we're going to unpack that more later, but right now we're just going to do some very, very simple transformations. And we want to see how the domain and range of our second function compare to the domain and range of the first function. That's called my parent function. Well, we've already done this work, so we don't need to do it again. When I plug in a -2, I get a 2. Plug in a -1, I get a 1, a 0, a 1, and a 2. Notice what this function here says. It says take whatever you got before and double it. Take whatever you got before and double it. So essentially, from here to here, all we're doing is multiplying everything by 2 because of this 2 right there. So the input is a -2 way over here, but then the output is going to be a +4 because I'm just doubling what I got before. If I double this one here, I get a 2. If I double this one, I get a 0. Double this one, get a 2. Double this one, get a 4. So let's look over here on the graph, how that's going to change things. Notice I don't get any negatives at all for the y, so I'm not going to even bother drawing much of that. So make sure to have a little bit of a scale on. Here's your x and y. I'm going to graph both of them. I'm going to use red for the parent function, f of x equals the absolute value of x. And I'm going to use blue for the new function, g of x, which is 2 times the absolute value of x. So the first one looks like this. The vertex there is at 0, 0. It bounces off the wall there. And this is what the original function looks like. Now what happens with the blue? At 2, instead of being here, at 2 being at 2, I'm at the 4, so I'm higher up. So right there. At the 1, I'm at a 2. The 0, I'm at 0. And it bounces off like so. And we get this. So, comparing these two functions, the parent function, which is the red one, the new function here, which has been stretched a little bit, pulled up. The first part says, how do the domain and range of the blue compare to the domain and range of the red? So let's see. Notice that I can put in the blue one here, all kinds of x's show up. I can be way in the negative, I can be way in the positive. And in terms of my y, what kinds of numbers come out? Look, everything still comes out. I still get a +1, a +2, a +3. All those still show up. So, here, there's no change in the domain or range. There's no change in the domain or range. If we were to look at this one down here, our parent, in goes a negative, out comes a positive, in goes a positive, out comes a positive. So again, our basic function looks like this, V-shaped. Okay. Entonces, this one, h of x, says this. Whatever we got before, just make it negative. Right? Don't you play that game with your parents? They tell you something, you say no. -2, -1, -0, no such thing. -1 and -2. So this function, although it has absolute value in it, it says take the opposite of what you get. That means everything is negative except for 0. So when I plot this puppy, I get these points here. Notice my colors work. You probably don't have colors on your paper. So when you draw this, you should label this appropriately so that you know it's not an X. If you're monochromatic, this looks like one big X. So let's just make sure we're labeling things, that this is my f of x. That's the f of x, the parent function. But down here is the h of x. Is that one there and that one there. If you have a highlighter or something or a color change, please make sure that this part, so we're not doing this. It's not all the way across like that. It's bouncing off. For this guy here, the domain, there's no change. No change here because it's still all real numbers. But there is a change in the range. How does the range change? So for h of x, the range is y is less than or equal to 0. So how does it change? It's the opposite and 0. It's the opposite and 0. The last thing we want to look at is something called rate of change. Now, we've already looked at rate of change in Algebra. Rate of change, of course, is just how things change. Now, in a line, it's also called the slope. So let's take a gander here. So we're going to look at the parent function, that is f of x equals absolute value of x. So this is the red line right here. And we want to know what is the rate of change between -3 and -1. So from here to here, what's the rate of change? So that's what we're analyzing. So let's see here. This rate of change right here. So all we really need to do is just figure out what our slope is, count our slope. So if we are considering this point right here to this point right here. So let's just count it off. We go down 1, down 2, so that's -2, and then right 1, right 2, so that's a +2. So counting that off, the slope here, or my rate of change, is down 2, right 2, and that simplifies to -1. Okay, now how does that change when we're talking about from 1 to 3? And we see, oh, instead of going down, we're now going up. So it looks the same steepness, just going up instead of going down. So just to count that one off, if I go from here to there, I just go up 1, up 2. So again, up 1, up 2, and right 1, right 2. So what does that mean? Well, that means this slope is up 2, right 2, which reduces to 1. So there we go. These are called the rate of change for that particular region. But I do want to point out to you that the rate of changes here, look, are the same but opposite. And one other thing is notice it's not written there, but the number that's in front there, the coefficient is a 1. Over here, the coefficient is a 2, and that's going to be telling. That's going to be telling. So let's see here. Now we're going to look at the blue line. What is the rate of change for g of x? Equals 2 times the absolute value of x for the same regions. So I've already marked those regions out, so now I'm going to count them differently. So let's see here. If I count this one out, and I'm going to start at this one and go up to here, so that goes up 1, up 2, up 3, up 4, so that's up 4, and left 1, left 2. So up 4, left 2, so the slope is up 4, left 2, which is -2. where else are we seeing that too? I don't know. Well, let's check the other one. So same idea here, but now we're going to go from this point right there to this point right here. So go up 1, 2, 3, and 4, up 4, and right 1, 2. There we go. So count this one off. My slope here is up 4, right 2, which is positive 2. Where else did we see that number? Oh, golly jolly. So look at this. It turns out that the coefficient here tells you about the slope. So that could actually help us to graph things quickly, kind of like slope-intercept form, which we'll look at later. But there we go. So your job now down here is to find the rate of change, between the same regions, but for the h of x there. Ready, set, go. And this concludes day 1 of absolute value function. Tomorrow, we'll pick up at domain and range, continuing on application. Have yourself a merry little absolute value day and interpretation.